Students, sir, few people are waiting in the lobby.
Please check my screen. Is it visible to all?
Yes,
Hello? Hello? Please check my screen. Is it visible to all?
Yes, sir.
Okay, thank you. This introduction to nanobiotechnology. Is it okay?
yes, sir.
Yes, sir. Visible.
Okay, thank you, beta. Thank you. Good morning to all. Yeah, two topics from unit second. Yeah, left introduction to nanobiotechnology, and second topic is nanomaterials in biotechnology. So these two topics I would like to complete today. Definition and overview, application, medicine, agriculture, and environment, future prospects. Yeah, what is nanobiotechnology? Combination of nanotechnology and biotechnology. When we talk about nano scale, means from 1 to 100 nanometer, uh, apply nanomaterials to biological system. यहाँ पर ऐड का कुछ नहीं आ रहा है, ये few students they are waiting. ऐड का कोई ऑप्शन नहीं दिखाई पड़ रहा है.
सर आप एक विंडो को माउस से हटा सकते हैं.
बेटा ये बच्चे कुछ वेटिंग में हैं, उनको ऐड करना चाहते हैं, इसमें कोई ऑप्शन नहीं आ रहा है. पहले था
सर ये ऊपर ये साइड वाले विंडो को आप क्रॉस कर सकते हो, ये इस पे हवर करने पे क्रॉस रहेगा.
ओके ओके ओके, थैंक यू. My screen is still visible. Hello. Hello.
Yes, sir. Visible. Yes, sir.
Okay, beta. So is this one materials at nano scale. 1 nanometer is equal to 10⁻⁹ meter. Unique physical and chemical properties, even thermal properties, electronic property. Physical property means thermal, electrical, electronics, all these, and then chemical property. What is biotechnology? Use of living organisms and biomolecules. Applications in medicine and agriculture. Uses DNA, means deoxyribonucleic acid. Then enzymes. Okay. So in fact, DNA is the fundamental molecule carrying genetic instruction for the development, functioning, growth, and reproduction of all known living organisms and many viruses. Then this one, enzymes are specialized biological polymers, typically proteins, sometimes RNA, known as ribozymes. Why nanotechnology? Biological molecules are nano-sized. All the biomolecules are in nano size. better interaction with cells, precise targeting possible. Properties of nanomaterials. I have already explained about nanomaterial. For example, carbon. If we take carbon nanotube and graphene, then all the properties I have explained related to carbon nanotube, and then graphene, because having high electrical conductivity, high thermal conductivity, and large surface to volume ratio. Okay, so large surface to volume ratio increase reactivity because of this. And then quantum effect. And quantum effect, again, phenomenon occurring at microscopic scales, atoms or electrons, that cannot be explained by classical physics. Okay, so where matter we have as both particle as well as waves. Then enhance strength because of nanomaterial, nanosize. Types of nanomaterials. Metal nanoparticle, for example, gold, silver. Okay, so these are metal nanoparticles. Then polymeric nanoparticle. Okay, and liposomes, in fact, commonly known as these lipid bilayer vesicles, are spherical closed structure composed of one or more phospholipid bilayers. Then carbon nanotube I have explained extensively. Then quantum dots also I have explained. Application in medicine. Targeted drug delivery. Yeah, there is no error during drug delivery. Cancer therapy. These are application of means nanobiotechnology. And gene therapy, diagnostics. So gene therapy, these are very much clear. So it's a medical technique that treats or prevents disease by modifying, replacing, or inactivating faulty genes within a patient's. Application in agriculture. Nano fertilizers. This is related with land. Then nano pesticides. In fact, nano pesticides are innovative pesticides. Formulation that incorporate engineered nanomaterials, typically 1 to 100 nanometer or up to 1000 nanometer, or used in nano technology-based delivery systems to enhance efficacy, stability, and targeted delivery. Then disease detection and improve crop yield. These again, crops, for example, rice, wheat, gram, all these improve crop yield. Means we can improve or enhance or increase this one crop. Then environmental applications, water purification, very much clear. Pollution detection, yeah. And then waste treatment. Yeah, this is largely research point of view. This is very, very important in recent years. Waste treatment. Advantage is targeted treatment, reduce side effects, early diagnosis. Okay. Challenges be in these years or in current years. Nanotoxicity. What is nanotoxicity? Refer to the adverse health effect and logical risk posed by nanomaterials. Particle again 1 to 100 nanometer in size on human health and the environment due to their high surface area to volume ratio and unique chemical properties. These particles can penetrate cell membranes, enter tissues, and cause damage such as oxidative stress or inflammation. Okay, high cost, of course. If you take example of MRI, it is very expensive. Regulatory issues, then future prospects. Personalized medicine, small drug delivery system, advanced biosensors. We have already explained about biosensors. So, nanomaterials or carbon nanotube graphene can be used for the detection of different biomolecules, including cancerous biomolecules, early detection, rapidly growing interdisciplinary fields, because these biotechnology, in fact, all chemistry and physics and even mathematics is also involved. So this is interdisciplinary field, and revolutionizing healthcare and diagnostic, require safety regulations. Okay, so this is related to nanobiotechnology. Okay. I think I have to stop this, then I can go in for another. Please check my screen. Is it visible to all? Hello.
Yes, sir.
Okay, thank you. Nanomaterials in biotechnology. Overview of nanomaterials and role in biotechnology application and future scope. Introduction to nanomaterials. I think I have explained several times. So material size 1 to 100 nanometer, unique physical and chemical properties, high surface to volume ratio. Often we call high surface to volume ratio. Any student can tell why we are saying high surface to volume ratio? Can explain any by any student? We are saying high surface to volume ratio. How?
सर डिनोमिनेटर में बहुत कम वैल्यू होती है तो वो न्यूमरेटर में आ जाती है और वो बहुत बड़ा हो जाता है अपना ओवरऑल वैल्यू.
कोई एग्जांपल ले लीजिए आप.
सर जैसे रेडियस नैनोमीटर्स में है तो 10⁻⁹ डिनोमिनेटर में आ गया, तो ऊपर 10⁻⁹ चला गया, तो सरफेस एरिया आर स्क्वायर हो जाएगा, वॉल्यूम आर क्यूब हो जाएगा।
वेरी गुड, वेरी गुड। अगर हम कोई स्फेरिकल पार्टिकल ले लें तो इसका सरफेस एरिया 4πr² डिवाइडेड बाई वॉल्यूम 4/3πr², तो 1/r आ जाएगा। ओके, 1/r आ जाएगा। तो 1/r इज इन द डिनोमिनेटर, r is the radius in nano size, so 10⁻⁹ it comes into the numerator, so 10⁻⁹. Okay, hello,
यस सर।
got it? 4πr² divided by πr³, 4/3πr³, so r 1/r आ जाएगा आपका उसका रिजल्टेंट, और फैक्टर उनको भूल जाओ। तो 1/r एंड r इज रेडियस, तो आपका r रेडियस अगर नैनोमीटर में है तो नीचे डिनोमिनेटर में 10⁻⁹, और ये ऊपर न्यूमिनेटर में आ जाएगा 10⁻⁹. So that's why high surface area to volume ratio. Okay. Compatible with biological molecules, enhance drug delivery, importance in biotechnology, improve diagnosis. Types of nanomaterials, metal nanoparticles, we can say gold nanoparticle, silver nanoparticle, polymeric nanoparticle, and liposomes have already explained. Then carbon nanotube, classification of carbon nanotube, single wall, multi-wall, properties of carbon nanotube. Okay, electrical, thermal, electronics, all these properties. Then quantum dot, again properties. And this one, polymeric nanoparticle. Polymeric nanoparticle are solid, biodegradable, and biocompatible colloidal particles ranging from 10 to 1000 nanometer in size. Okay. Metal nanoparticle, okay, gold nanoparticle, silver nanoparticle, and then used in imaging and antimicrobial applications. Polymeric nanoparticle, biodegradable polymers, controlled drug release, targeted therapy. Liposomes, lipid bilayer vesicles, encapsulation of drugs, reduce toxicity. This, in fact, lipid bilayer vesicles, commonly known as liposomes, are spherical, closed structure composed of one or more phospholipid bilayers, and these vesicles often 25 nanometer to 1 micrometer size. Carbon nanotube, many properties, high strength and conductivity, used in biosensors. We have already explained about this. Drug and genes delivery. Semiconductor nanocrystals, bright fluorescence, used in bioimaging. Application in medicine. Targeted drug delivery, cancer therapy, genes therapy, tissue engineering. Targeted drug delivery is very much clear. Cancer therapy is very much clear. Genes therapy is a medical technique that treats or prevents disease by modifying, replacing, inactivating faulty genes within a patient cells. Tissue engineering, this is another very important topic in recent years, is an interdisciplinary field combining engineering, material science, and life sciences to develop biological substitute that restore, maintain, or improve tissue function. Okay, so tissue engineering, this is another separate topic of this biomedical applications. Application in diagnostic biosensors. Okay, using biosensors, we can detect various biomolecules, early disease detection, imaging techniques. Imaging technique are diagnostic methods used to visualize the interior of the body, allowing doctors to detect, diagnose, and treat illness by creating images of organs, tissues, and bones. Common methods include X-rays for bones, CT cardio scans for cross-sectional views, magnetic resonance imaging, MRI, for soft tissues, and ultrasound for real-life imaging. Then application in agriculture and environment. Many, this I think is repetition, water purification, pollution monitoring. I think pesticides are innovative pesticide formulation that incorporate engineered nanomaterials, typically Ubuntu. I think this is also repetition. Nanofertilizers are advanced nutrient carrying particles designed on a nano scale that enhance agriculture efficiency through control, slow release, and improve plant uptake. Advantages of nanomaterials: high efficiency, target specificity, and reduce side effects because of these nanomaterials. Challenges and risks: nanotoxicity. What is nanotoxicity? Refer to the adverse health effect and toxicological risks posed by nanomaterials, particle size, this one, on human health and the environment. Due to their high surface area to volume ratio and unique chemical properties, these particles can penetrate cell membranes, enter tissues, and cause damage such as oxidative stress or inflammation. Then environmental impact, then regulatory concern. Future perspective: personalized medicine, smart nano devices. Phone is also a smart device, nano device, because you can use anything. You can use as a computer, you can use as a television, you can use as a signal detector. So this is also a smart nano device kind of. Advanced biosensing systems, yeah, can detect any signal even from a distant object. Nanomaterials play a vital role in biotechnology, expanding application in healthcare and environment, requires safe and ethical usage. Okay, so these two topics were left. I think I have explained carbon nanotube field effect transistor for carbon nanotube field effect transistor based biosensor for the detection of various molecules, but I have not sent literature. These two topics today I have explained. I shall send you this PPT. And you can prepare your notes according to your syllabus. Please check my screen. Is it visible to all?
Yes.
Okay. So I have this one discuss carbon nanotube field effect transistor based biosensor for the detection of various molecules, and this is another graphene field effect transistor based biosensor for detection of various cancerous biomolecules. These are the outlines. Graphene and carbon nanotube synthesis methods. I have already explained. Plasma enhanced chemical vapor deposition or microwave plasma enhanced chemical vapor deposition. I have already explained about this. Graphene field effect transistor introduction, then types, device structure, theoretical modeling, result and discussion, conclusion, application of the Yenberg. So in fact, graphene, this is nanostructure material, is a single atomic plane of graphite and is sufficiently isolated. I think I have already explained about graphene. You can wrap up into zero-dimensional buckyballs rolled up into one-dimensional carbon nanotube or nanotube, and stick into three-dimensional graphite. Okay, so this is in fact 2D graphene. You can roll it up into single this one single wall nanotube, or this is multi-wall nanotube, coaxial kind of. So because of these properties, okay, single sheet of carbon atoms of all graphitic form, different configurations leads to formation of buckyballs, nanotube, and graphite. They discovered this 2D graphene in the year 2004, and they were awarded Nobel Prize in the year 2010. Because of these properties, this material is very important. Thinnest and highly transparent, 98% transparency of graphene. If you have observed just in the back side of DTC bus, that sheet is graphene sheet kind of structure. If you observe that, strongest material, intrinsic strength is around 120 gigapascal. 1 giga means 10 raised to 9. Pascal means 1 pascal 10 raised to -2 torr. And in comparison to steel, 860 megapascal. So this is higher than this, much higher. So strength, okay, strongest material. Highest current carrying density, 10 raised to 8 ampere per centimeter square, in comparison to copper, 10 raised to 6 ampere per centimeter square. Excellent conductor of heat, 5000 watt per meter per Kelvin, in comparison to diamond, 300 watt per meter per Kelvin. Okay. So these are the, in fact, graphene synthesis methods I have already explained. These are the method: laser ablation, arc discharge, and in fact, first time this one carbon nanotube fabricated using arc discharge, but here I am interested only in plasma enhanced chemical vapor deposition. This is another technique. This is thermal chemical vapor deposition. Because many advantages using this technique, we can get vertically aligned carbon nanotube or graphene using PECVD or MPCVD. So these are the synthesis or fabrication methods. Okay, laser ablation, chemical vapor deposition, then thermal chemical vapor deposition, and plasma enhanced chemical vapor deposition. Here we use this PECVD technique, then we can get vertically aligned carbon nanotube or graphene. And this is in fact MPCVD technique. I have taken this schematic diagram from Professor B.D. Banker, Physics Department, IIT Delhi. So I have already explained about how to grow carbon nanotube and graphene using this technique. So first we grow nano size catalyst film. Now, what are the catalyst? Catalyst means iron, cobalt, nickel. Iron, cobalt, nickel. Just you take iron and grow nano size film using thermal evaporation or electron beam evaporation or RF discharge or sputtering, DC or RF sputtering technique. Okay, then place that film, nano size film. First we grow nano size, for example 10 nanometer catalyst film, iron film, on silicon substrate, then put that nano size film over here, and then create plasma. Now, this is in fact microwave plasma enhanced chemical vapor deposition technique. Microwave generator. So this microwave generator of frequency 2.45 gigahertz and power 500 to 600 watt. So this frequency is fixed. Even for house, we use microwave oven. The frequency is fixed, 2.45 gigahertz. Okay. So now create plasma. For example, nitrogen plasma, okay, or ammonia plasma, and this is plasma. So irradiate or expose that nano size film in presence of plasma. What you will get after exposing or irradiating, because you can maintain this substrate temperature. Here, this is substrate with catalyst. Okay, so substrate temperature, because plasma either 1 electron volt or even 0.5 electron volt. 1 electron volt is equal to 1.15 into 10 raised to the power 4 Kelvin. So means plasma is this much of temperature. Okay, so it maintains the substrate temperature, number one. Number two, by exposing this catalyst film in presence of plasma, we can get nanoparticle. Means that nano size film converted into nanoparticle, which we required for the growth of carbon nanotube and graphene. Now, after 10 minutes, inject hydrocarbon gases. Hydrocarbon gases either methane, CH4, or ethylene, C2H2, or C2H6. Okay, along with dilution gases. Dilution gases means hydrogen or argon. When these hydrocarbon gases go inside, in presence of this plasma, what will happen? This dissociate. So, for example, CH4 or C2H2, when it dissociates inside the plasma, carbon and hydrogen separated. So, carbon come on that nano size nanoparticles. Okay, so that we can get graphene initially, and then because of this plasma, or this is in fact plasma sheath, not plasma. Plasma in fact two types, bulk plasma and plasma sheath. So bulk plasma and plasma sheath both are different, because in case of bulk plasma, that quasi-neutrality condition holds. What is quasi-neutrality condition? Quasi-neutrality condition says electron density approximately equal to ion density. I think just take this one. Yeah. So this is bulk plasma and this is plasma sheath. So in case of bulk plasma, this quasi-neutrality condition satisfied. And quasi-neutrality condition says ion density approximately equal to electron density. But in case of plasma sheath, because plasma sheath is formed in both the devices. Here this is plasma sheath. This is plasma sheath in PECVD and MPCVD. So plasma sheath. So that process is occurring in presence of plasma sheath. So in plasma sheath, that condition doesn't hold. Quasi-neutrality condition doesn't hold. And this condition doesn't hold, it means a lot. Because if you take Maxwell's first equation, divergence E is equal to rho upon epsilon. Rho is volume charge density. It can be rewritten as minus Ne into E plus Ni into E. For electron, minus Ne into E, density into electronic charge. And for ion, density into electronic charge. So minus Ne into E plus Ni into E, right hand side. Left hand side, E is equal to electric field is equal to minus gradient of potential. E is equal to minus grade phi. Substitute it. So minus del square phi is equal to right hand side minus E upon epsilon Ne minus Ni. Something density difference, right hand side. Because of left hand side del square phi, left hand side potential, right hand side density difference. Because of that density difference gives potential difference, and that potential difference gives electric field, and that electric field gives force. and that force is responsible for getting vertically aligned carbon nanotube and graphene. This is physics. Okay, how we can get vertically aligned carbon nanotube or graphene? So because of this, in fact, I am taking these two technique, PECVD or MPCVD, because we can get vertically aligned carbon nanotube and graphene. Okay, and these are the parameters of this plasma sheath. These are the plasma sheath, electric field sheath, width, Debye length. This Debye length again related to plasma parameter. This is electron temperature, this is electron density. And then this is in fact sheath width, again related to this one, these parameters. And Debye length, and then substrate biasing, then electron temperature, then ion and electron current density. These are the parameters in plasma sheath. So we can get vertically aligned carbon nanotube or graphene using this. Okay, so this is MPCVD about MPCVD. Similarly, this is in fact PECVD. Here we can use this RF electric field. RF electric field means 13.56 megahertz in place of this microwave, and glow discharge occurs. This is RF power. Again, plasma sheath is formed, and the rest procedure is same, because using this technique we can get vertically aligned nanostructure. Nanostructure means carbon nanotube and graphene. Okay. Now this first electronic computer, in fact, so much of vacuum tubes, crystal dies, relays, resistors, and these. So energy needs to be conserved to protect our environment from drastic changes, to save depleting resources for our future. So it is important for use to realize how energy is useful to us and how can we avoid it getting wasted. And first electronic computer was made in the year 1943. Then MOSFET scaling and Moore's law. I believe that everybody is aware about MOSFET, means metal oxide semiconductor field effect transistor scaling, Moore's law. So this is in fact scaling means this, gate length as a function of here. So just you can see here micrometer, and then point. If you come here 20, so this is in fact 0.0 something. So this is here means nanometer. And then, of course, around 20-30 picometer. So because size is, gate length is reduces. Gate length is reduces. What are the advantages? Because these are the resultant laptop and these. Okay. High packing, faster switching, low power consumption, decreased cost. Okay, these are the advantages for this gate length reducing. Now, battery technology is not speedy. Why so much of it is on device scaling? Portable devices run on battery. Battery life is limited, and battery technology is not improving at the same speed as that of very large scale integrating circuit, VLSI. So either use bigger battery or reduce power consumption. Okay. We can reduce, and short channel effect also important. By reducing short channel effect, we can increase this one efficiency of device or electrical properties like drain current, transconductance, output conductance. These are electrical properties of a transistor and cutoff frequency. So this is single gate MOSFET, a source, drain, gate. Okay. And then double gate here, front gate and back gate, source, drain. Okay. This is tri-gate or FinFET, third same. And then gate all around MOSFET, cylindrical kind of gate all around. So higher surface area for channel. If you use this one, graphene or carbon nanotube as a channel, so higher surface area for channel, greater controllability. over channel, the short channel effect can be reduced. This is using carbon nanotube and graphene as a channel. Need of gate all around in MOSFET as we are moving towards nanoscale technology. The transistor density is increasing. So downscaling of transistor is required, but reducing the transistor size leads to degradation in device performance. This degradation is due to short channel effect, such as sub-threshold current, drain-induced barrier lowering, etc. Several structures such as double gate, tri-gate, I have already explained, have replaced MOSFET. So gate-all-around structure have the advantage of strong control over channel by gate in contrast to multi-gate FET. It has highest conductivity and electrical properties. Okay. Now, introduction to graphene field effect transistor. Here, graphene as a channel. This is graphene as a channel. Substrate, then graphene as a channel, then oxide layer, source, drain, and this is gate. This is in fact a reference. I have taken this structure from this paper. Large signal performance of graphene FET considering contact resistance. Okay. Then type of graphene, GFET, graphene field effect transistor. This is top gate. This is in fact back gate. And this is dual gate, top gate and back gate. Then introduction to this one, carbon nanotube field effect transistor. I think I have already explained here. Source, drain, and we have replaced this one carbon with the silicon channel. Okay, and rest is same. These are type of carbon nanotube field effect transistor: back gate, dual gate, wrap around gate, suspended, and then biosensing mechanism. This is, in fact, this device we want to fabricate. This is bioreceptor. Analyte. It could be any biomolecules, could be enzyme or any aptamer cells, anything, any biomolecules. Come in contact with bioreceptor. This is in fact recognition site. Then it convert into biochemical signal and use transducer. It can convert biochemical signal into electrical signal. Okay, and this is electronic. Then you can convert analog to digital because your detector can accept only digital signal. So then electrical signal this can detect, and you can plot current as a function of voltage. Okay, so this is in fact. So how we can use nanomaterials for biosensing applications, or this is because of or why we use these graphene and carbon nanotube based in field effect transistor for fabrication of this one biosensor for the detection of various biomolecules because of chemical stability, high electrical conductivity, high surface to volume ratio, most mechanical strength, biocompatibility. These are because of these the properties of nanomaterials. Now this is in fact work my students has done. Graphene nano engineered plasma tailored dielectric interface field effect transistor for detection of breast cancer biomarkers. So this is in fact drain source, and this one is graphene as a channel. Okay, back gate. This is top gate. So this is dual gate. why we are using this one, graphene as a channel? Because high value of drain current, high transconductance, high on-off current ratio, lower channel resistance, better control over channel formation, high efficiency. So this schematic diagram I have taken from this reference. Field effect transistor based on single layer graphene and graphene drive materials. Now this is our structure. In fact, a student prepared this is structure. This is source, drain. This is graphene as a channel. Then we have used hafnium oxide in place of silicon dioxide. Advantage of hafnium oxide, using hafnium oxide is because of high this one permittivity around 22, and silicon dioxide permittivity 3.9. This is in fact source length, this is drain length, and this is channel length, graphene channel, and this is semiconducting materials. So again the same because of these advantages. Okay, this is a lump capacitance representation, hafnium oxide gate and gate source capacitance, gate drain capacitance, source drain, and graphene as a channel. These are the biomolecules, cancerous biomolecules we have taken. Cell type MCF 10A, permittivity 4.5, healthy. HS578T, permittivity 22, unhealthy and cancerous. T47D, another biomolecule, permittivity 32, healthy and cancerous. Now, these are the biosensor specification and parameters. This is graphene based, okay, and this is silicon based. We have compared our result with silicon based. Channel thickness in nanometer, same. Channel length in micrometer, 0.1, same. And source dimension is also same for graphene and for silicon based. And drain dimension is also same. Oxide thickness, hafnium oxide thickness 1.5, here also 1.5. So this length of cavity is also same. Then we have this one simulated our results, and in fact this is this black one is experimental result and red one is our simulated result. So simulation results almost comparable to the experimental result. Drain current as a function of gate voltage for these parameter. Drain source voltage 1.0 and channel length 100 nanometer, source length 200 nanometer, and drain length 200 nanometer, and thickness of that oxide 1.5 nanometer. Okay, so experimental data were adopted from Simonescu et al. And while the simulated curve was generated using cell-by-CoTCAD, a close correlation between the two confirmed the reliability of the proposed simulation. Then this is in fact graphene based result, this is silicon based result. Of course, those biomolecules, no biomolecule, this result. Then this one permittivity 4.5 and this one permittivity 22 and this is permittivity 32. So by increasing permittivity, just you can look at these schematic diagram, this drain current and the function of. मैं अभी क्लास ले रहा हूं, मैं अभी बात करूंगा, ठीक है? This just we can see by increasing permittivity, this drain current increases. Here also by increasing permittivity, drain current increases, because here this is permittivity 4.5, this is permittivity 22, here permittivity 32, this one. Okay, and these are the parameter: drain source voltage, then channel length, source length, drain length, and thickness of oxide. So we can see by increasing permittivity, this one, drain current increases. Here also drain current increases, but these results are better than this one. Just we can compare. Then transconductance as a function of gate to source voltage. Again the same. These biomolecules, this is black one is no biomolecules, then red one 4.5, then this one 22, and green one 32. So this by increasing permittivity, this transconductance increases. This is another property of electrical property of a transistor. Okay. So this is in fact transconductance, del IDS upon del VGS, derivative of drain current. So the changing the transconductance versus the change in VGS for the proposed device, transconductance is the first derivative of this. Then drain current is a function of drain voltage for the same biomolecules, same parameters. Here this is graphene based, this is silicon based. Again, here results are better than this silicon based. Then we have calculated sensitivity. Sensitivity analysis of proposed biosensor. In fact, sensitivity is defined by on current with biomolecules minus on current without biomolecules divided by on current without biomolecules. Then on sensitivity as a function of dielectric constant of biomolecules. Just we can see 4 point, this is in fact red one is graphene based device and this one is silicon based device. 4.5 means without biomolecule. 4.5 means without biomolecule. This is graphene based and this is silicon based. Now come to this. This is 22 HS578T and this is graphene based and this is silicon based. Then come to T47D, permittivity 32. So this is in fact graphene based, this is silicon based. So just we can see the sensitivity also increases with the increasing permittivity of biomolecules. Okay. Another problem also my students has done this one too, the graphene field effect transistor for biosensing applications, plasma induced semiconductor 2D graphene field effect transistor. This is in fact device is same source drain and this one also. Here this is in fact graphene channel as a channel, this is heater, this is substrate, plasma sheath. The device is structure and this is in fact simulated result, same experimental and then simulation results. Okay, using silvicoticate. Then we have developed a model. In this case, in fact, we have considered graphene as a 2D this one potential profile derived by Wechofer et al. The potential profile of 2D semiconductor plane for a line charge perturbation located at x is equal to 0 with one dimensional charge density of this one Qn delta comma 1d with device length lambda d. So potential is given by Q n delta 1d upon 2 pi epsilon 0 x log lambda d upon x. Now epsilon 0 x, this one stands for the permittivity of the oxide layer. Here Q is equal to minus C, electronic charge. And if we substitute to x is equal to T, thickness of the graphene sheet, here we substitute to x is equal to T and Q is equal to minus C, then this if we calculate this one thickness, then this is the expression. So what is lambda d? Yet main focus is lambda d. In fact, device length related to various plasma parameter like electron temperature T ion temperature Ti, ion number density Ni, electron number density Ne, electron pressure Pe, and ion pressure Pi. So this is the standard expression for Debye length, 1 upon lambda d square is equal to 1 upon lambda d square plus 1 upon lambda di square, where this electron Debye length is given by epsilon 0 kT upon Ne0 E square half, and ion Debye length is equal to epsilon 0 kTi upon Ni0 E square 1 by 2. So substituting these values, so we can calculate lambda d. It turns out this one. So these are the electron temperature, ion temperature, electron density, ion density. So Debye length is a function of plasma parameter. Now, if Debye length is a function of plasma parameter, this is function of plasma parameter. It means T is a function of plasma parameter. Thickness of a channel. Here we have used graphene as a channel. Now, thickness of graphene sheet can be related to plasma parameter this way. Okay, so T now is substituting the value of lambda d in this equation. So this thickness can be rewritten as this one. Now, this expression of the thickness of graphene sheet can be utilized in the expression of drain current using this. Another expression is the drain current is equal to electronic charge density, mu mobility, W width of the graphene sheet, and L length of the channel, and BDS, this is drain source potential, and T the thickness. So using this, the value of T from this to here. So drain current is a function of plasma parameter, also function of width of the channel, also function of length of the channel, and you can study the role of plasma on electrical property of a transistor, like drain current you can calculate. You can also calculate transconductance, you can also calculate output conductance, you can also calculate this one, cutoff frequency, all these parameters you can calculate. Okay, so here drain current is a function of plasma parameter, also width of the channel and length of the channel. Another expression for drain current is given by mu omega W upon L. This is in fact capacitance of oxide. This is gate voltage. This is drag point voltage, VDP, and this is drain source voltage. So in fact, drain current is a function of this length and width, and this approximately equal to this one. So drain current is also function of this plasma parameter and gate voltage, width of channel, length of the channel. So then we have done the calculations. In fact, we have done calculation for plasma assisted catalytic growth and field emission property of graphene. We have already studied and published a paper in the year 2015. So use parameter from this paper. So electron parameter, then 1, this is electron density, 2, electron temperature, this is ion density, this is ion temperature. Okay. So by increasing plasma parameter, just look at this table. By increasing plasma parameter, this channel length decreases. Okay. So here drain current is a function of gate voltage for different biomolecules. This is MC of 10A, then HS578T, then T47T. Okay, here permittivity, 0 permittivity, then 4.5, then 22, then 32. Then transconductance is a function of gate to source voltage for different biomolecules, these cancerous biomolecules. Again, same results. This is in fact graphene based, this is silicon based. Then we have studied this is sensitivity for graphene based and for silicon based. Of course, graphene based results are better. Then drain current is a function of gate to source voltage. And transconductance is a function of position along the channel. Then we have taken this one, channel thickness 17 meter. Earlier we have taken channel thickness 15 nanometer, here 17 nanometer. Then we have taken 19 nanometer. Okay, and we have studied this one sensitivity for three. So the impact graphene nano-engineered plasma tailored dielectric, this one interface field effect transistor for ultra-sensitive detection of breast cancer biomarkers, and on-off current ratio is this much, and this in fact enhancement was found to be this percentage increase in on current, this percent improvement in on-off current ratio. So this work is in upgrading the graphene field effect transistor is a strong contender for high performing ultra sensitive biosensing, especially for breast cancer detection. Okay, so electrical properties like threshold voltage, transconductance, output conductance were noted for varying values of plasma parameters corresponding to various values of channel thickness at fixed channel length. So if you have any question or any doubt, then you can discuss. So application of this work is for the detection of various biomolecules, for example, protein, DNA, antibodies. These are the references. So if you have any doubt or any question, you can discuss. Now only unit 5 is left, and which I am planning to do after the midterm or during online classes. Okay. Rest of the syllabus I have completed. If you have any doubt, any question, you are most welcome at any time.
सर मिड सेम का क्या सिलेबस है
बेटा?
मिड सेम में कितने यूनिट्स आएंगे?
यूनिट 5 है, तो यूनिट 5 अभी 5th यूनिट हमने करवाया नहीं है और 4 यूनिट हमने करवा दिए। अब आप देख लीजिए कि यूनिट, देखिए यूनिट फर्स्ट है वो प्लाज्मा प्रोडक्शन एंड डायग्नोसिस। एक क्वेश्चन वहां से हम पूछेंगे, हाउ कैन यू प्रोड्यूस प्लाज्मा यूजिंग PECVD और MPCVD टेक्निक, एंड हाउ कैन यू मेजर प्लाज्मा पैरामीटर्स यूजिंग लैंग्वेज प्रूफ टेक्निक। एक क्वेश्चन यहाँ से आएगा कोई भी डिवाइस के बारे में। एंड देन आपका सेकेंड यूनिट है प्लाज्मा नैनो टेक्नोलॉजी, उसमें आपका कार्बन नैनोट्यूब एंड ग्राफीन से रिलेटेड क्वेश्चन पूछा जाएगा। तो उसमें what is carbon nanotube, types of carbon nanotube, properties of carbon nanotube, application of carbon nanotube. Similarly, what is graphene, 2D graphene, and एक यहाँ पर और हम पूछ सकते हैं, how can you fabricate or grow carbon nanotube or graphene using PECVD और MPCVD technique, ये हम पूछ सकते हैं यहाँ पर। और ये प्रॉपर्टी वगैरह यहाँ पर यही चीजें हैं। और आज जो हमने 2 टॉपिक करवाए, नैनो मटेरियल्स इन बायोटेक्नोलॉजी और एक है एक ऊपर था इंट्रोडक्शन टू नैनो बायोटेक्नोलॉजी, ये टॉपिक दो रह गए थे और तुमने सारा करवा दिया है। तो ये यहाँ पर कार्बन नैनो ट्यूब और ग्राफीन एंड देन क्वांटम डॉट नैनो वायर, इससे रिलेटेड यहाँ पर है। अब आप मुझे, ये 2 यूनिट हो गए और थर्ड यूनिट जो है वो बायोसेंसर से रिलेटेड है, जिसमें हम व्हाट इज बायोसेंसर, कंपोनेंट ऑफ बायोसेंसर, हाउ इट वर्क। तो यहाँ से ये हम आपको पेपर अभी भेजते हैं, जो हमने 2 टॉक दिए हैं। एक तो कार्बन नैनोट्यूब फील्ड इफेक्ट ट्रांजिस्टर बेस्ड बायोसेंसर फॉर डिटेक्शन ऑफ वेरियस बायोमॉलिक्यूल, और दूसरा हमने दिया आज ग्राफीन फील्ड इफेक्ट ट्रांजिस्टर बेस्ड बायोसेंसर फॉर डिटेक्शन ऑफ वेरियस बायोमॉलिक्यूल। इनसे रिलेटेड हम पेपर भेज देते हैं। बस यहीं तक रखते हैं यूनिट 3 तक, ठीक है। यूनिट 4 और 5 नहीं, हम 4 के बाद नहीं, यूनिट 3 तक हो जाएंगे। हमें 5 क्वेश्चन डालने हैं, और ठीक है। इज इट ओके?
गुड आफ्टरनून सर।
हाँ बोलिए।
सर एटलीस्ट सर टू यूनिट सर थोड़ा बेटर रहता सर, थोड़ा स्कोरिंग हो जाता। लाइक सर मिड सेम में सर थोड़ा अपॉर्चुनिटी रहती है स्कोर करने की।
अच्छा 2 यूनिट तक। फिर आप मिड टर्म, वो एंड टर्म में तो बहुत सिलेबस हो जाएगा।
सर एंड टर्म में कर लेंगे सर, थोड़ा मिड सेम में स्कोरिंग अपॉर्चुनिटी रहता है सर। तो प्लीज अगर आप हो सके तो इनिशियल 2 चैप्टर्स दे दीजिए।
भाई यहाँ तक ये यूनिट फर्स्ट से एक ही क्वेश्चन बनता है, यूनिट फर्स्ट से। अब यूनिट सेकंड से एक कार्बन नैनोट्यूब का हो गया, एक ग्राफीन का हो गया। चलो क्वांटम डॉट और नैनो वायर।
सर वो थोड़ा यूनिट 1 सर थ्योरेटिकल है सर, थोड़ा सा उसको पढ़ लेंगे सर, थोड़ा डीप नॉलेज हो जाएगा। एंड सर लाइक फेस्टिवल भी रहेगा सर लास्ट वीक, तो सर थोड़ा सर उसमें भी सर टाइम वगैरह सर नहीं मिलेगा ना ज्यादा सर पढ़ने का। ऑनलाइन क्लासेस रहेंगी लास्ट
और
वीक।
दूसरे बच्चों को बोलने दो। मैं केवल एक बायोसेंसर से रिलेटेड क्वेश्चन डालना चाहता हूं, तो आप डालें ना डालें, दूसरे बच्चे बोले।
सर यूनिट 2 तक ठीक रहेगा सर।
ठीक रहेगा, तो चलो डन। यूनिट सेकंड तक मिड टर्म का सिलेबस। ओके
ओके सर।
ओके। ओके अटेंडेंस प्लीज। रोल नंबर 2।
सर उसका सर वो लीव हो गया, तो सर वो प्रेजेंट था सर क्लास में, रोल नंबर 2।
अच्छा तो ओके ओके ओके। रोल नंबर 4।
प्रेजेंट सर।
आपकी भाई बहुत एब्सेंट हो रही है, क्या है, क्या बात है? रोल नंबर 6।
Present, sir.
रोल नंबर 7, 9,
Present, sir.
10, 12.
12 present, sir. 12 present, sir.
Okay. 15.
सर 15 प्रेजेंट है, उसने चैट में लिख दिया।
Okay. 16, 19, 22,
सर प्रेजेंट।
22.
प्रेजेंट सर।
Okay. 23, 26, 27.
26 present, sir.
26 present. Okay. 27.
27 present, sir.
28. 29.
Sir, 28 present था सर, like सर अभी भी है सर, मे बी माइक वर्क नहीं कर रहा होगा.
Okay.
28 present है.
33.
33%, sir.
34.
34 present, sir. 34 present.
38.
सर उसके माइक में इशू है सर 38 पे.
Okay. 40.
Present, sir. Present, sir.
रोल नंबर 40.
Present, sir.
आपको
Present,
क्या
sir.
हो गया? आपको क्या हो गया बेटा? रोल नंबर 40 आपको क्या हो गया? नॉट ए सिंगल अटेंडेंस.
नहीं सर, आया था पहले मैं क्लास में, लेकिन क्लास में आ रखा हूँ.
आप हमसे मिलने आना, हम आपका दिखा देंगे.
Okay.
41.
41 present, sir.
43.
Yes, sir. 43 present, sir.
47. 48.
Sir, 48 present, sir.
49.
Present, sir.
50.
Present, sir.
51.
सर 51 present.
आपकी बहुत एब्सेंट है. 52. 56.
तो present था sir. So 52 present था sir.
अच्छा 52 प्रेजेंट है. ओके. 56. 57. 59.
Present, sir. 59.
आप भी बहुत आपके एब्सेंट हैं. रोल नंबर 60.
Present, sir.
63. 64. 65.
65 present, sir.
66.
सर 66 का माइक नहीं चल रहा.
ओके. 68.
Present, sir. 68.
71. 73. 74.
Present, sir.
78. 81. 82. 83. 85. 89.
89 present, sir.
90.
90 present, sir.
आपकी बहुत एब्सेंट है. शुभम, क्या बात है?
Yes, sir.
91. 92. 93. 95. 96.
96 present, sir.
97.
97 present, sir.
99.
Present, sir. 99.
104. 105. 106.
Present, sir.
106.
Yes, sir.
आप क्या रास्ता भूल गए आज क्या? उज्जवल यादव.
सर वो एक्चुअली मैं इंटर्न पे था अभी, तो मैं कॉलेज अभी ज्वाइन किया है.
किस पे थे आप?
मैं इंटर्न कर रहा था एक जगह, तो मैंने कॉलेज अभी ज्वाइन किया. मैंने कोई भी क्लासेस नहीं ली हैं.
तो आप अटेंडेंस लोग क्या करेंगे? आपको एग्जाम देने देंगे क्या? क्यों? 108. आप एप्लीकेशन लिख के दें. 109.
Sir 109 present.
112.
Present, sir.
113, 115 और किसी के रह गया होगा? अच्छा अभी और हैं बच्चे. ओके 118.
Present, sir. 118.